So I introduced this last time. I introduced it on Monday, and I derived some things by hand. We're going to go through it again. I think that it always helps to see this in more than one way and to repeat it. So the Fetkevich method, what Fetkevich did is he attempted to derive another model, and I say in addition to Van Everdeen and Hurst, that was less tedious than that model. So we knew that VEH was very accurate, but it was also very tedious. And so Fetkevich says, well, what if I come up with something that's almost as good, almost as accurate, but is a lot simpler? And that method did not require the superposition principle that we had to use in VEH. So in his model, he assumes pseudo-steady state. That's why I use the PSS. So PSS stands for pseudo-steady state. So it ignores the infinite acting flow part. It's only talking about the later time. So that's one limitation, but it's still quite good. And that's what I say here. It's a very good approximation of Van Evergreen and Hurst. And in the example we do on Friday, I'll actually show you that when you compare the two, they're like within 5% of each other or something. So how was this model derived? Okay, I think it's always important to understand where equations come from. Because if you don't, then you don't really know what the limitations of those are or how to do something a little bit different if the problem is a little bit different, so if you needed to derive something new. So it's good to understand where these problems come from, these equations come from. So the first thing is that we're going to recall the total encroachable water, meaning the amount of water that would encroach the reservoir from the aquifer over very long time scales is given by this equation, which was effectively the small pot aquifer. Wi is the pore volume of the aquifer. CF and CW were the formation and water compressibilities. Sometimes we just, instead of doing CF plus CW, we'll say C sub T. It's a total compressibility. PI is the initial pressure, and PA bar is an average aquifer pressure. So it's this pressure drop. And it makes sense, right? The bigger the pressure drop, the more water that would encroach. So again, that's initial pressure and that's average aquifer pressure. We could rearrange this equation and solve for PA bar, the average aquifer pressure, in this way. So it's equal to PI times 1 minus WE. WE is the total encroachable water, and WEI is just this new variable which I've defined as a total compressibility times WI times PI. So if you don't quite see that, then multiply this through and substitute WEI and rearrange for PA bar and see that you get the same thing. So this is PA bar. So the average pressure is equal to the initial pressure times 1 minus this cumulative water divided by this constant here. And what we want, we're talking about time, how things change with time. So we want to take the derivative of pressure with respect to time. Or I should say the derivative of the water influx with respect to time. So it's dWE dt, right? This is the rate at which water comes in, because WE is cumulative amount, so the change in the cumulative amount with respect to time is like a water rate. And if you take the derivative of this equation here, dWE dt, or you do it up here, either way, then WEI and PI are constants, but PA, that's the aquifer pressure, will change with time, right? And so that's what I have over here. Now I do have this negative sign in there, which I put in red font. The reason is because the original PowerPoint file I had on there didn't have that negative sign. I noticed before class that it was a typo, so I've added it, and I will be sure to upload these onto PowerPoint. But I've put it in red font so that you notice that there's been a change there, a correction. Okay, so what did Fetkevich do? Well, Fetkevich made an assumption. He said, well, what if the water rate, the water that comes from the aquifer into the reservoir, is proportional to the drawdown pressure, the difference between the aquifer pressure and the reservoir pressure? P is the reservoir pressure. Okay, and then there's some sort of constant proportionality that's J. Now, he didn't just completely come up with this out of thin air. In fact, this equation should look very familiar to you. should be very familiar to you from Reservoir 1 as well as the review video that you watched for last Friday's quiz. In that, we said that during pseudo-steady state flow from the reservoir into the wellbore, Q, is proportional to the pressure drop between the reservoir and the wellbore times a constant J, a productivity index. This looks almost identical to that. So again, we've got this analogy here where the aquifer to the reservoir is analogous to the reservoir to the wellbore. So Fetkovich made this assumption. I'll show you what J is in a moment. We'll just say it's a constant, but it's very similar to the calculation we had in Reservoir 1 for flow into a wellbore. But this is the water rate, which is a change in WE with respect to time. J is a constant proportionality. This is the difference between the aquifer pressure and the reservoir pressure. So then what Fetkovich said is, well, I've got this equation for dWe dt, and I've got this equation for dWe dt. Let's equate them. So when he equated those, you'll see that we got the left-hand side was that our first equation we had for dWe dt, and the second equation is that pseudo-steady state assumption that Fetkovich made. And you'll need an initial condition to solve this ODE, which is the aquifer pressure is equal to PI. So okay, this is an ordinary differential equation. All right, so we want to solve for PA as a function of time. PA appears here and PA appears there. If you remember ordinary differential equations, one common way to solve these is by separation of variables. So you move all the PA's to one side, you move all the T's to one side, and when I separate those variables, this is what I get. So I move this PA bar minus P over to the left-hand side, so you get 1 over PA bar minus P times dPA. And over on the right-hand side, JPI and dWEI are all constants. They don't need to go in the integral since they're constants. And I integrate from 0 to T of dt. There is no other time, so this integral is going to be super simple, right? It's just going to be T. I did put this in red font because I think there was a little typo both in my handwritten notes last time in the PowerPoints. This is supposed to be not dP, but dPA. So the pressure of the aquifer, not the pressure of the reservoir. But if you integrate the right-hand side, that one's really easy. The integral of dt is just t. So that's why I have minus JPI WEI times time. The left-hand slide is slightly more complicated, but I think that most of you remember from your calculus class that the integral of 1 over x is the ln of x. And for the same reason here, the integral of 1 over PA minus P is the ln of PA minus P. And then you've got these constants of integration, so you get this. And so when you plug that in, and then you could take the exponential of both sides, and you get this solution. Okay. So I encourage you to do this yourself after class, maybe rewatch the video if you need to. But this basically says that PA bar, that's the average aquifer pressure, minus the reservoir pressure, is equal to the initial pressure minus the reservoir pressure times E to this minus this constant times time. Okay, and so what that kind of implies is the aquifer pressure is declining exponentially, and maybe, you know, and so that sort of makes sense. So we've got this, and what are we going to do with that? Well, if we go back the previous slide, or even up to there, we recall what Fetkovich said is that dWe dt is J times, I'm going to call this a drawdown pressure, it's the pressure between the aquifer and the reservoir, is equal to that. But now I have an expression for PA bar minus P, which is this one right here. So I can take this equation and substitute it into there. And that's what I'll do in this next slide. So dWe dt is equal to J times this drawdown pressure. And making that substitution with our solution, we have JPI minus P e to this constant times time. And of course, at time is equal to 0, no water has it came into the reservoir, right? That'll happen later. So that's an initial condition. Okay, so we already solved one ordinary differential equation. Now we have a new one. dWe dt is equal to this. So you got time there and you got time there. So you can think of, and so what we want to solve is for WE as a function of time. That's really what we wanted all along, right? What we've wanted all along is to solve for the cumulative amount of water that comes into the reservoir as a function of time. So if we solve this WED, we'll get WE of time. This might look like a tough ODE to solve, but it's really not. Because all this says is this is a derivative is equal to a constant, e to a constant times time. And so you separate your variables, you move the dt over the other side. What you need to do is you need to take the integral of this term on the right. And so I said this last time, but what's the integral of e to the x? Okay. Because we're in video stream, I can't get feedback, but I'm guessing that most of you recall that the integral of e to the x is e to the x. That's pretty simple. What's the integral of e to the 4x? Well, it's 1/4 e to the 4x. Okay, and so in this case, that's basically what you have. You got a constant e to a constant times time, or if you prefer x. So when you do that integral, you get WE of t is equal to WEI over PI, PI minus P times this term in parentheses. And again, I highly encourage you to do that integral yourself and prove to yourself that this is what you get. So, if t is 0, then e to the 0 is 1. You get 1 minus 1 is 0, so the amount of water that comes into the aquifer, to the reservoir, is 0 at time is equal to 0. That was our initial condition. But as t goes to infinity, this term goes to 0, which means 1 minus 0 is this, and then you're left with this. By the way, that's the small pot aquifer, right? So at t goes to infinity, you get that, and I think that's the case. So, but in between, you get this equation here. Okay, one catch with this. This would be true if the reservoir pressure was dropped to a constant pressure P and stayed there for the remainder of the time. So let's say we have an initial pressure, 5,000 psi, and then we drop the pressure to 4,000 psi, and then it stayed there. Well, this would be sufficient. Okay, but we know that that's not really what happens with the reservoir pressure. We know that the reservoir pressure just doesn't just drop all at once and then stay there. What it does is it declines with time. So P is a function of time. And that's tricky, and we will have some data there. We will have some data of pressure versus time that will be given to us. I mean, I keep on saying this, but basically you'll have a well bore or multiple well bores. You'll have pressure gauges in there. You can measure the reservoir pressure. There's multiple wells. You can average those, and that gives you a really good estimate of the reservoir pressure. So you'll have that, time versus pressure, but it's not constant. It's declining with time, and that makes it a little bit trickier, okay, because what do you use for P? Well, we do something similar as to what we did with the VEH model, and that is that we assume that pressure drops in step changes. So you'll be given a table of pressures, and you assume that pressure, that's the reservoir pressure for a certain period of time, and then it drops, and then there's another period of time, etc. And so what we do is we say that the change in water influx, so basically the incremental amount of water that's encroached the reservoir, is given by this equation, which is sort of a correction or alteration of this equation over here. So instead of WE of T, what we say is that the incremental amount of water that's been encroached since the last time step is WEN. WEI and PI are the same. We're not going to use the initial pressure anymore. We'll use the pressure of the aquifer at the last time step. So if T were equal to 0, then this would be PI. But if we're later on, then this is the pressure at the beginning of this new interval. That's why it's PA bar N minus 1, where N is the interval. So N minus 1 is the previous time step. P bar N is the average reservoir pressure at this time. And then this is very similar as to what we had up there, except that I'm going to do a delta T, which is the change in time, you know, the time interval that we're doing over here. So if we're going from 1,000 hours to 1,200 hours, then delta T would be 1,200 minus 1,000. So this is the incremental water influx during that period of time, and you can add up all those incremental water influxes and get a cumulative amount. So how do you calculate PN bar? That's that average reservoir pressure. It's an average, so it's pressure at the last time interval times plus the current time interval divided by 2. And again, we'll have this data in a table. And then what about PA N minus 1? So the aquifer pressure, average aquifer pressure at the previous time level, we can calculate that as equal to the initial pressure times 1 minus WEN over WEI. So at time is equal to 0, WEN was 0, so then PAN minus 1 is equal to PI, which is kind of what we had over here. So to kind of recap what we're doing here is that as the reservoir pressure drops for different time periods, in each one of those time periods we calculate a cumulative amount, we calculate an incremental amount of water influx, and then we sum all those up to get a cumulative amount, WE. The big advantage of the Fetcovich method is you don't have to use that principle of superposition. So what I tried to communicate before when we were talking about the VEH method was that when we wanted to calculate the cumulative water influx at a given time, we would have to do this superposition and add these times up and get an answer. But then if we wanted to calculate the cumulative amount of water influx at a previous or later time, we'd have to redo the whole calculation again. And I do that in that video, and again, please watch that video of that example problem. But for the Fetcovich method, we don't have to worry about that. So to kind of review, the steps for doing the Fetcovich method are as follows. First off, you calculate the initial encroachable water WEI and the productivity index J. So WEI is given here. Okay, 5.614 converts things from cubic feet to barrels. Use the right units there. And J, I didn't share with you what J is yet, but it's given by this over here. So J is over there. You know, anytime you see these what appear to be random numbers in front of these equations, that's usually, almost always, a conversion factor that allows you to just use oil field units in your equation. So a mistake I see a lot of people make, in fact, I've seen it on the homework a few times when people have talked to me, is that they try to do the unit conversions, but you don't need to because they're already built in there. So you just need to be in the right oil field units. If you have days, you might have to convert that to hours, but otherwise you use millirc for permeability, etc. So that's WEI and J. Then we initially set the reservoir pressure at the end of the nth time step to PN bar and the average pressure to equal to PI. Okay. Then we calculate the average pressure during the time step. That was given by this equation here. We calculate the water influx during that time step, which is this WE. And then we calculate the cumulative amount, which is the sum of all these incremental water influxes. and then we're done. So, and then finally you can calculate the new aquifer pressure using the equation PI times 1 minus WEN divided by WEI. So this is all a little confusing. That's okay. That's why we're going to do an example problem on it on Friday. Also, I think that this table here is somewhat helpful. Okay, so I'll spend a couple minutes on this table, and if you need to go back and rewatch it and pause the video, then please do that. So what do we have? What you're going to be given is these first two columns. Time, likely in hours, and pressure of the reservoir at those times. So you get PI, P1, P2, P3, P4, all the way to the last time that things were measured. And we can create this table. So an Excel spreadsheet is a good way to do this. Certainly you could write a Python code as well. And at the beginning, your average reservoir pressure is going to be equal to PI. Your average aquifer pressure is going to be equal to PI. And obviously we won't have encroached any water into the reservoir yet, right? So nothing happens before time 0. So what happens at time 1? Well, we can calculate a new average reservoir pressure, which is the initial pressure plus the current pressure divided by 2. So it's an average of these two. The difference between the average aquifer pressure and Pn is going to be this Pi minus this P1 right over here, this P1 bar. WE, delta WE, the incremental amount of water, is going to be given by the equation we had before. And we know everything in that equation now. Okay, presuming that you've calculated J and WEI. So you get your delta WE. This is the incremental water that was encroached between 0 and T1. And then WE1 is this delta WE, so what we calculated here, plus 0, right? This is the cumulative amount. So it's this plus what was the cumulative before, so that's 0. And then you can calculate a new average aquifer pressure, which we'll use in the next time step. And then you repeat this on all of your rows, but in each time, your new cumulative water is equal to the incremental water, this delta WE, plus the cumulative in the previous time step. And so then you add all of these up. Okay. So a table or Excel spreadsheet is a nice way to do this. A Python code might be more efficient, but I think a spreadsheet's a good way to visualize it and to really demonstrate, really understand the problem better. So one thing I will point out is that the delta T's here are the change in time. So it's T1 minus 0, or T2 minus T1, or T3 minus T2, T4 minus T3, etc. That is different than how we did our delta T's for the Van Evergreen and Hurst method. Okay, and I won't review that now, but we talked about it on the last two videos, so I'd go back and do that. But effectively, it's always the final time step, so like a Tn minus a T0, or Tn minus T1, or Tn minus T2. So do make sure you understand the difference there between the Van Evergreen and Hurst, or VEH method, and the Fetkovich method. Okay, so I promised that that this was the case before, and I think that this is the exact example problem that we'll do on Friday. But what I have here is a plot of the water influx and reservoir barrels, the cumulative water influx, versus time in days. And so it looks like it's a year or two period. And this is the Fetkovich versus the VEH method. So they are very close. They're not exactly the same, but they're very close. And the VEH method is a little bit more accurate, but it's a lot more work. And everything we do as engineers is some sort of approximations. And we were sort of making estimates or guesses as to things like porosity and thickness and other things. So there's already some error built into that anyway. So the Fetkovich does a really good job, right? And so maybe you'd want to do the VEH method as well. But if you wanted to do a quick calculation that took 5 or 10 minutes, then maybe you do the Fetkovich to kind of get an initial estimate. And then the VEH method might take you an hour or two, and you get the more accurate method. But I'm a big believer in doing things multiple ways as an engineer. I mean, I would never want to make a big time decision for the company I work for based on one calculation. And then the second thing is I'm a big believer in doing short, quick calculations first, and then doing the more complicated ones. In fact, I would probably do the small pot aquifer first, and that would sort of be the upper bound, because I know that would be the maximum amount of water if you waited long enough. One other thing I'll say about these is that how do we calculate J? Well, I alluded to it before. We've got this conversion constant. K is in millidarcies, H is the thickness in feet, F is that factor, that's the angle divided by 360, so if you've only got partial of a reservoir, then that would be less. Mu W is the viscosity of water, RA and RE are the radius of the aquifer and reservoir respectively, and then we got this minus 0.75. That would be for radial flow, so those are those concentric cylinders, and if you got a closed outer boundary. And I circled it in red because that's the one that we will probably use the most. But there are some adjustments for linear flow or if you have an open boundary at the edge. If I don't say otherwise, you can use this one in red, or you could, if I don't say otherwise, you could say, well, I'm going to assume that this is a no-flow closed reservoir and use this, right? And then you get this J in barrels per PSI per day. And that makes sense because J gets multiplied by a pressure drop, which is PSI, so then you're left with barrels per day, and J times this pressure drop is a rate. It's a barrels per day. Okay, so that's the Fetkovich method. I'd like to talk about one last thing, and this is sort of applicable for all our models. Or there are a few other models out there, but those are the popular ones I discussed today. But one thing is history matching. And history matching, I want to talk about this because it's not just important for aquifers, but it's really important for all aspects of reservoir engineering. And it's something that reservoir engineers do a lot of, and if you take Reservoir 3, Reservoir Simulation with Dr. Foster as an elective, he might talk about history matching as well. What is history matching? Well, we use a lot of models, and we use those models to make predictions. Those models are very useful, okay? But there's a saying that scientists and engineers use that says that all models are wrong, some are useful. And so this is not an exception either for any of the models that we use. And why is that? Well, first off, the equations themselves are built on some assumptions. I mean, Fetkovich, I mentioned that he assumed pseudo-steady state flow and ignored infinite acting flow. Even the VEH method assumed a radial reservoir and some other things in there. But there's another thing in there which is probably a more important aspect, which is that we needed to have inputs. I needed to give you the porosity of the aquifer, the permeability of the aquifer, the thickness of the aquifer, the viscosity of the water, the size of the aquifer and the size of the reservoir. And those are things that we can estimate. We can estimate them with well logs. Many of you are taking a well logging right now. We could take them with core samples. So if we drill a well, we can grab some of the rock and measure the permeability. There are other techniques we can use. But there's a lot of uncertainty there. Especially, that's true in reservoirs, but it's especially true in aquifers. Because as I mentioned a couple weeks ago, we don't generally drill wells into aquifers. All right, doesn't make money to drill a well into a water aquifer. And if you're not drilling wells, then it's difficult to do any type of logging or to grab any core samples. So what we probably do is assume that they have the same properties as the adjacent reservoir, which may or may not be true. So what is history matching? History matching is effectively adjusting the parameters of your model in such a way that it matches the historical values. So what I'm really trying to say is that you have a model, and then maybe you're able to determine what the model is trying to predict, like water influx, a different way. And in our case, it'll be from the material balance equation. And if you're lucky, then the model and the actual match up really well. If they don't, then you can tweak your model or the inputs of your model to match the actual data. And then, so then your question is probably, well, what good is that? What good is the model if you have to, what good is a model for past data, for past historical data? Well, once you do that tweak, once you make that change so that it matches the past data, now you have more confidence that things like your permeability, porosity, thickness, compressibility, etc., are accurate, and you can use that model with more confidence to predict the future, which is really our job as reservoir engineers. It's to predict the future. So, okay, so how do we compute WE another way to get the actual value? Well, one way to do that is the material balance equation. So remember, the material balance equation can be written this way. Okay, and I moved everything over to the right-hand side except for WE. WE we know increases with time. F is the production of fluids. Of course we're going to know that, right? We're going to measure the oil produced, the gas produced, and the water produced at the surface. GFGI is related to the original gas in place. It's really the gas in the gas phase. NFOI is the oil in the oil phase. It's related to the original oil in place. You learned a few different ways in Reservoir 1 to determine those. You could do it from past data, or you can use it from volumetrics, which basically means you use a contour map that a geologist gave you and to estimate that. But if we have GFGI and NFOI, and we can measure, we can get EGWF and EOWF because those are PVT properties, and we have F, that means we have everything on the right-hand side of the equation as a function of time. F is, of course, a function of time, so everything over here is a function of time, and then you get WE of T. So now you have a second way of measuring WE of T, and you can compare your model, WE model, whether it be the VEH method, the Fetcovich method, the Schlitthuss method, with what you get from the actual data. And so when you get that match, if they don't match, either the wrong model is used, and you might want to try a more accurate one. So if you used the Schlitthuss method, maybe you want to try Fetcovich or VEH. Or the assumed aquifer properties, like the permeability, porosity, etc., were wrong. If you are confident in the model, let's just say you use the VEH and you know that's super accurate, then what you can do is you can adjust uncertain aquifer properties. You might have more confidence in some properties than others. So water viscosity. You'll have a really good idea of what that is. I mean, we know that water, the viscosity of water is 1 centipoise at room temperature. It is a function of temperature, but that's published on the internet and tables and everything else. And so you're going to know what the aquifer water viscosity is, plus or minus 5%. So that you might be really confident in. The permeability, maybe not so much. Maybe you assumed it was 100 millidarcies because that's what the reservoir permeability was, but you don't know that the rock pore structure or rock type didn't change when you got to the aquifer. So that might be something you're less confident in. And so what you can do is you can adjust those until your model and data match better. One thing that can be done is, let's presume you have an undersaturated oil reservoir. So there's no gas phase, and is the original oil in place, and then this is what the model looks like. You can rearrange this to make some plots. So let's presume that you know the original oil in place, N, and you compute WE of T by solving for that with data. Then you can plot WE of T divided by EOWF versus F over EWF. And if you get a nice straight line with a 45-degree angle, then WE was correct, then your model was correct. If it sort of veers up, then WE is too small. If it goes this way, it's too large. If it does something funny like this, then maybe you had the incorrect geometry. Maybe it wasn't truly a radial reservoir or something. But that's one thing that can be done. So yeah, you plot this on the y-axis, you plot this on the x-axis. The slope should be 1, that's why you get a 45-degree angle, and the intercept is the original oil in place, N.